universe is screaming at us, but we can barely hear a whisper. Deep in the mountains of West Virginia, the Robert C. Byrd Greenbank telescope stands like a colossal ear pressed against the cosmos. Its dish, spanning 100 meters across, tilts slowly through the night sky, collecting invisible signals that have traveled billions of years to reach Earth. But step into the control room and you'll hear something that might surprise you. Not the melodic beeps and whistles that Hollywood loves to portray, but something far more chaotic, static, pure, overwhelming static. This is the sound of cosmic noise, and it's everywhere. Radio telescopes don't actually make sounds on their own. The crackling, hissing symphony you hear is the universe translated into audio frequencies that human ears can perceive. Every pop and whistle represents electromagnetic radiation, streaming from distant stars, galaxies, and cosmic phenomena we're only beginning to understand. It's like standing in the middle of Times Square during New Year's Eve, trying to have a conversation with someone whispering from across the street. For decades, scientists have been listening to this cosmic cacophony, searching for something extraordinary hidden within the mundane. They're part of SETI, the Search for Extraterrestrial Intelligence, a scientific endeavor that began in earnest in 1960, when astronomer Frank Drake pointed a radio telescope at two nearby stars and listened for artificial signals. He heard nothing but noise. Drake's experiment, called Project Ozma after the queen of the fictional land of Oz, marked humanity's first serious attempt to eavesdrop on alien civilizations. The logic was elegant in its simplicity. If intelligent beings elsewhere in the galaxy had developed radio technology as we had, they might be broadcasting signals into space, either intentionally or as a byproduct of their civilization. All we had to do was listen carefully enough. But therein lies the challenge. The universe is not a quiet place. Every second, trillions of radio waves wash over Earth from natural sources scattered across the cosmos. The sun hurls charged particles in our direction, creating radio interference that can disrupt communications here on Earth. Distant pulsars, the collapsed cores of massive stars, spin like cosmic lighthouses, beaming radio signals in precise intervals as they rotate. Quasars, supermassive black holes feeding on matter from their host galaxies, blast radio energy across billions of light years with the power of 1 trillion suns. Even the universe itself contributes to the din. The cosmic microwave background, the afterglow of the Big Bang, fills every cubic centimeter of space with faint radiation. It's the universe's baby picture, taken when it was only 380,000 years old and cool enough for atoms to form. This ancient light, stretched and redshifted by cosmic expansion, creates a constant background hum that radio telescopes detect no matter where they point. Against this overwhelming backdrop of natural radio chatter, SETI researchers face a daunting task. They're looking for signals that might be artificial, created by intelligent beings using technology. But how do you distinguish between a natural radio source and one created by an alien civilization? How do you separate the cosmic wheat from the chaff? The problem becomes even more complex when you consider the sheer scale of the search. Radio waves span an enormous range of frequencies, from extremely low-frequency waves that can penetrate deep underground to gamma rays with frequencies so high they can punch through solid matter. SETI researchers must decide where to listen in this vast electromagnetic spectrum, knowing that they can't monitor everything at once. Early SETI efforts focused on what scientists call the waterhole, a relatively quiet region of the radio spectrum between the emission lines of hydrogen and hydroxyl. The reasoning was both scientific and poetic. Hydrogen is the most abundant element in the universe, and hydroxyl is a key component of water. Together, they form H2O, the molecule essential for life as we know it. Perhaps, the thinking went, Intelligent beings would recognize this cosmic significance and choose to broadcast in this naturally quiet frequency range. But even within the waterhole, the universe is far from silent. Natural radio sources still dominate, and the signals that SETI researchers hope to detect would likely be incredibly faint by the time they reach Earth. A radio transmission from a civilization orbiting Alpha Centauri, our nearest stellar neighbor at 4.3 light-years away, would arrive at Earth billions of times weaker than the radio signals we routinely detect from our own satellites. The challenge is like trying to hear a whisper from across a football stadium filled with people shouting at the top of their lungs. Except the stadium is the size of the galaxy, the shouting never stops, and you're not even sure if anyone is whispering at all. This overwhelming noise has shaped every aspect of SETI research, from the design of radio telescopes to the algorithms used to process data. Engineers build receivers capable of detecting signals so faint they barely register above the thermal noise generated by the electronics themselves. Computer scientists develop pattern recognition software that can sift through millions of radio frequencies simultaneously, searching for the telltale signatures of artificial signals. Yet despite decades of technological advancement, the fundamental challenge remains unchanged. In 1977, astronomer Jerry Ehman was analyzing data from Ohio State University's Big Ear Radio Telescope when he noticed something unusual. A strong, narrow band signal had appeared in the data, lasting exactly 72 seconds before disappearing forever. Ehman was so struck by the anomaly that he circled it on the computer printout and wrote "wow" in the margin. The wow signal, as it came to be known, remains one of the most intriguing detections in SETI history and one of the most frustrating. Here was a signal that appeared artificial in every measurable way. It was extremely narrow in frequency, unlike the broad-spectrum emissions typical of natural radio sources. It appeared at the hydrogen line frequency, exactly where SETI researchers expected to find alien transmissions. And it came from a region of sky devoid of known stars or planets, suggesting it originated from somewhere far beyond our solar system. But the signal never repeated. Follow-up observations of the same region found nothing. No telescope since has detected anything similar. The wow signal exists as a single, tantalizing data point in 40 years of SETI observations, neither confirmed nor explained away. This is the reality of searching for alien signals in cosmic noise. Every detection is ambiguous. Every signal could have a natural explanation, and every promising candidate seems to slip away upon closer examination. It's a field where the absence of evidence dominates the landscape, where researchers must remain scientifically skeptical while privately hoping for the discovery that would change everything. The noise isn't just a technical challenge, it's a fundamental part of the cosmic environment that any spacefaring civilization would have to navigate. If aliens are out there broadcasting radio signals, they face the same problem we do. Their transmissions would have to compete with all the natural radio sources in the galaxy, from their own star to distant quasars billions of light-years away. This realization has led some SETI researchers to wonder if we're approaching the problem from the wrong angle entirely. Maybe advanced civilizations don't broadcast powerful beacon signals into space, hoping someone will hear them. Maybe they've learned to work with the cosmic noise rather than against it, hiding their communications in the natural radio environment in ways that would be nearly impossible for us to detect with current technology. After all, if you wanted to communicate across the galaxy without advertising your presence to potentially hostile neighbors, you might choose to make your signals look exactly like cosmic noise. You might embed your messages in the natural radio environment, creating a form of cosmic steganography that only someone who knew what to look for could decode. This possibility opens up an entirely new frontier in SETI research, one where the cosmic noise isn't an obstacle to overcome, but a medium to explore. It suggests that alien signals might already be hidden in the data we've collected over decades of observations, waiting for us to develop the right techniques to extract them from the overwhelming background of natural radio emission. But first, we need to understand just how loud and chaotic that background really is. To understand why finding alien signals is so difficult, you need to appreciate just how spectacularly noisy the universe really is. It's not just loud in the way a construction site or rock concert is loud. The cosmos generates radio waves with energies that dwarf anything humans have ever created, broadcasting across frequencies that span the entire electromagnetic spectrum with a persistence that never stops. Our own sun, that seemingly peaceful ball of gas 93 million miles away, is actually a violent radio transmitter. Every 11 years, it goes through a cycle of magnetic activity that can unleash radio storms powerful enough to knock out satellite communications and disrupt power grids on Earth. During solar maximum, when the sun's magnetic field is most active, it can produce radio bursts that are millions of times stronger than the most powerful transmitters humans have ever built. These solar radio emissions aren't just brief outbursts. The sun constantly streams charged particles into space at speeds exceeding 1 million miles per hour, creating what scientists call the solar wind. When this wind interacts with planetary magnetic fields, it generates radio noise that can mask weaker signals from more distant sources. Jupiter, with its massive magnetic field and radiation belts, produces radio emissions so strong they were first detected by radio astronomers in the 1950s, long before anyone expected planets to be radio sources. But solar system radio noise is just the beginning. Look beyond our cosmic neighborhood, and the universe reveals itself to be an even more chaotic place. Pulsars are among the most precisely timed objects in the universe, yet they're also some of the most disruptive radio sources. These rapidly rotating neutron stars, typically only 12 miles across but containing more mass than our Sun, sweep beams of radio energy across space like cosmic lighthouses. The Crab pulsar, the remnant of a supernova witnessed by Chinese astronomers in 1054, spins 30 times per second, producing radio pulses so regular they were initially mistaken for artificial signals. When Jocelyn Bell first detected pulsars in 1967, she and her supervisor Anthony Hewish briefly considered the possibility that they had found evidence of extraterrestrial intelligence. The signals were so precisely timed and appeared so artificial that they nicknamed the first pulsar LGM-1 for Little Green Men. Only after discovering several more pulsars did astronomers realize they were observing a previously unknown type of stellar object, not alien transmissions. This discovery highlighted a fundamental challenge in SETI research. Natural astrophysical phenomena can produce radio signals that appear artificial, at least initially. The universe is full of processes that generate narrow band signals, precise timing, and other characteristics that SETI researchers associate with technological origin. Distinguishing between natural and artificial signals requires not just detecting unusual radio emissions, but understanding them well enough to rule out exotic astrophysical explanations. The challenge becomes even greater when you consider the most energetic radio sources in the universe. Quasars, powered by supermassive black holes consuming matter at phenomenal rates, can outshine entire galaxies in radio wavelengths. The most distant quasars detected by astronomers are so far away that their light began its journey when the universe was less than 1 billion years old. Yet they're still bright enough to be seen across 13 billion years of cosmic time. These distant powerhouses don't just produce steady radio emission. They can vary dramatically in brightness over periods ranging from hours to years, creating radio signals that might initially appear artificial to automated detection systems. A quasar flaring up could easily mimic the characteristics of a powerful alien beacon, at least until astronomers could identify its true nature through careful observation and analysis. Even more mysterious are fast radio bursts, or FRBS, which have become one of the most intriguing phenomena in modern astronomy. These millisecond-long flashes of radio energy were first discovered in 2007, hidden in archival data from the Parkes Observatory in Australia. The first FRB was so brief and energetic that it took years for astronomers to convince themselves it was real and not some kind of instrumental glitch. FRBs are extraordinary by any measure. In just a few milliseconds, they release as much energy as our Sun produces in several days. They appear to come from cosmological distances, billions of light years away, yet their radio emission is concentrated in such narrow time windows that they seem almost designed to be noticed. Some FRBs repeat irregularly, while others appear only once and never again. The discovery of FRBs sent ripples of excitement through the SETI community, not because anyone seriously thought they were alien signals, but because they demonstrated how little we still understand about high-energy astrophysics. If the universe could produce radio phenomena as exotic as FRBs, what other surprises might be hiding in the data? Most FRBs are now thought to originate from highly magnetized neutron stars, called magnetars, which can generate magnetic fields trillions of times stronger than Earth's. When the crust of a magnetar cracks under the stress of its own magnetic field, it can release more energy in 1/10 of a second than our Sun produces in 100,000 years. But even with this explanation, many aspects of FRBs remain mysterious, and new discoveries continue to challenge astronomers' understanding. The cosmic microwave background adds another layer of complexity to the radio landscape. This ancient radiation, left over from when the universe first became transparent to light, fills all of space with a faint but persistent signal. At 3 degrees above absolute zero, it's incredibly cold by human standards, but it's warm enough to generate thermal noise that radio telescopes detect as a constant background hiss. This background radiation isn't perfectly uniform. Tiny fluctuations in temperature, typically less than 1/10,000th of a degree, reveal the seeds of structure that would eventually grow into galaxies and galaxy clusters. These minute variations create subtle patterns in the cosmic microwave background that can interfere with searches for much weaker artificial signals. The situation becomes even more complicated when you factor in our own galaxy. The Milky Way is pervaded by magnetic fields and cosmic ray particles that interact to produce synchrotron radiation across a wide range of radio frequencies. This galactic radio emission varies with direction, being strongest when looking toward the galactic center and weaker when observing in directions perpendicular to the galactic plane. Radio astronomers have learned to work around these natural sources through careful observation planning and sophisticated data analysis techniques. They avoid observing near-strong radio sources when searching for weak signals, and they use multiple telescopes to confirm detections and rule out local interference. But even with these precautions, the natural radio environment sets fundamental limits on what kinds of signals can be detected. Consider the challenge facing any SETI signal trying to make its way through this cosmic obstacle course. An alien transmission from a star system 100 light-years away would first have to compete with radio emission from its own host star. Then it would have to traverse interstellar space filled with charged particles and magnetic fields that could scatter or absorb the signal. Upon reaching our solar system, it would encounter the solar wind and Earth's own magnetic field, which could introduce additional interference. Finally, when the signal reaches a radio telescope on Earth, it would have to be distinguished from terrestrial radio interference, atmospheric effects, and instrumental noise. The entire electromagnetic spectrum around Earth is filled with human-made signals, from cell phone towers and Wi-Fi networks to radar systems and satellite communications. Radio astronomy sites go to extraordinary lengths to minimize this interference, often locating telescopes in remote areas with strict limits on radio transmissions. The National Radio Astronomy Observatory's Green Bank facility, for instance, sits within the National Radio Quiet Zone, a region covering more than 13,000 square miles, where radio transmissions are heavily regulated. Even microwave ovens and diesel engines are restricted in the immediate vicinity of the telescope, because their electromagnetic emissions could contaminate astronomical observations. Yet despite all these efforts to create quiet observing conditions, the natural cosmic radio environment remains overwhelmingly noisy. A typical SETI observation might collect data across millions of frequency channels simultaneously, searching for narrow-band signals that stand out above the background noise. But in those millions of channels, natural astrophysical sources can create thousands of false alarms that must be investigated and ruled out. This is why SETI researchers have developed increasingly sophisticated algorithms to automatically classify radio signals. Modern SETI programs use machine learning techniques to distinguish between natural astrophysical sources, terrestrial interference, and potentially interesting unknown signals. These algorithms can process terabytes of data in real time, flagging unusual detections for human review, while automatically discarding the vast majority of signals that have clear natural explanations. But even the most advanced algorithms struggle with ambiguous cases. A signal might have characteristics that are consistent with either a natural source or a technological origin. It might appear at frequencies where both pulsars and hypothetical alien transmitters could operate. It might show timing patterns that could result from either astronomical phenomena or artificial modulation. This ambiguity is compounded by our incomplete understanding of high-energy astrophysics. The universe regularly surprises astronomers with new phenomena that don't fit existing theoretical models. Gamma-ray bursts, magnetar flares, and fast radio bursts were all completely unknown just decades ago. What other exotic astrophysical processes might be lurking in the data, masquerading as potential alien signals? The discovery of exoplanets has added yet another dimension to the cosmic radio environment. We now know that planetary systems are common around other stars, and many of these systems likely contain gas giant planets with strong magnetic fields similar to Jupiter. These exojupiters could be significant radio sources, potentially producing emissions detectable across interstellar distances. Some astronomers have even suggested that radio emissions from exoplanets could serve as a new SETI target. If alien civilizations have developed powerful transmitters, they might use their planet's natural radio emissions to mask artificial signals, broadcasting in frequencies where natural planetary radio emission would provide perfect camouflage. This possibility illustrates how the cosmic noise problem cuts both ways. While natural radio sources make it difficult to detect alien signals, they also provide opportunities for advanced civilizations to hide their communications. A sufficiently sophisticated alien species might deliberately choose to operate in frequency ranges dominated by natural sources, making their transmissions nearly indistinguishable from cosmic background noise. The result is a cosmic radio environment of staggering complexity, where natural processes generate signals across every frequency band that SETI researchers might want to monitor. From the constant whisper of the cosmic microwave background to the explosive roar of gamma-ray bursts, the universe broadcasts with an intensity and persistence that makes our most powerful transmitters seem like whispers. Understanding this natural radio landscape is essential for anyone hoping to find alien signals hidden within it. It's not enough to simply listen for unusual radio emissions. SETI researchers must become experts in astrophysics, learning to recognize the signatures of pulsars, quasars, magnetars, and dozens of other cosmic radio sources. They must understand how interstellar space affects radio propagation, how our own galaxy contributes to the background noise, and how terrestrial interference can mimic signals from space. Only by mastering this cosmic cacophony can researchers hope to identify the faint whisper of an alien civilization trying to communicate across the vast distances between the stars. The universe may be loud, But somewhere in that overwhelming symphony of natural radio emission, there might be a single artificial note waiting to be discovered. The most sensitive ears humanity has ever built for listening to the cosmos are mechanical marvels that dwarf most buildings and rival suspension bridges in their engineering complexity. These radio telescopes represent our species' greatest attempt to overcome the cosmic noise problem through sheer scale, precision, and technological sophistication. For decades, the undisputed champion of radio astronomy was the Arecibo Observatory in Puerto Rico. Built into a natural sinkhole in the tropical mountains, its 305-meter dish was so large it could have held 3 football fields side by side. The receiving equipment suspended above the dish on cables was positioned with millimeter precision, despite hanging 150 meters above the reflector surface. Arecibo wasn't just big, it was extraordinarily sensitive. Its enormous collecting area allowed it to detect radio signals billions of times weaker than what smaller telescopes could observe. When CT researchers used Arecibo to search for alien signals, they were working with an instrument capable of detecting a cell phone transmission from the nearest star system. The telescope's sensitivity came from fundamental physics. Radio waves are incredibly faint by the time they reach Earth from distant sources. A typical radio signal from a quasar billions of light years away delivers less energy than a snowflake hitting the ground. To detect such weak signals above the thermal noise generated by the receiver electronics, radio astronomers need collecting areas measured in acres, not meters. Arecibo's massive dish collected radio waves across its enormous surface and focused them onto receivers cooled to within a few degrees of absolute zero. These cryogenic receivers reduced thermal noise to the absolute minimum possible, creating instruments so sensitive they could detect the heat signature of a human being on the moon. But even Arecibo had limitations. Built in the 1960s, it could only observe sources that passed overhead as Earth rotated. Unlike optical telescopes that can point anywhere in the sky, Arecibo's dish was fixed in place, constraining observations to a strip of sky roughly 40 degrees wide. This limited its effectiveness for systematic SETI surveys, which ideally would cover the entire sky with equal sensitivity. The telescope's receivers were also limited by the technology available when it was constructed. Early radio astronomy equipment could only monitor relatively narrow frequency ranges, forcing researchers to make difficult choices about where to search in the electromagnetic spectrum. A SETI observation might cover just a few million frequency channels, a tiny fraction of the radio spectrum where alien signals could potentially hide. Despite these constraints, Arecibo contributed to some of the most significant SETI observations in history. It was used to listen to nearby star systems for artificial signals, to conduct all-sky surveys for unusual radio sources, and to follow up on promising candidates detected by other telescopes. When the WOW signal was detected in 1977, Arecibo was one of the telescopes used in unsuccessful attempts to detect it again. The collapse of Arecibo's receiver platform in December 2020 marked the end of an era in radio astronomy. But by then, a new generation of radio telescopes had already begun to revolutionize the field. The most impressive of these is the 500-meter aperture spherical radio telescope, known as FAST, nestled in the mountains of southwestern China. FAST dwarfs even Arecibo in collecting area. Its 500-meter dish could contain nearly 2 Areteibos, giving it almost 3 times the sensitivity for detecting weak radio sources. But FAST's advantages go beyond mere size. Unlike Arecibo's fixed dish, FAST can change its shape slightly by adjusting the positions of thousands of individual panels, allowing it to point more precisely at different regions of the sky. The engineering challenges involved in building FAST were extraordinary. The dish surface consists of 4,450 individual triangular panels, each precisely positioned by computer-controlled actuators. The entire structure weighs more than 1,000 tons, yet it must maintain its shape to tolerances measured in millimeters as it tracks sources across the sky. FAST's receivers represent the cutting edge of radio astronomy technology. They can simultaneously monitor frequency ranges spanning several gigahertz, processing billions of channels of data in real time. Modern digital signal processing techniques allow FAST to search for multiple types of signals simultaneously, looking for continuous wave transmissions, pulsed signals, and broadband emissions all at the same time. But even FAST, impressive as it is, represents just one approach to the sensitivity problem. Another strategy involves combining multiple smaller telescopes into arrays that can achieve the sensitivity of much larger single dishes. The Very Large Array in New Mexico consists of 27 individual antennas, each 25 meters in diameter, spread across the high desert in a Y-shaped configuration. When the VLA antennas work together, they can achieve the sensitivity of a single dish, 130 meters across. But their real power lies in their ability to create detailed radio images of cosmic sources. By precisely timing the arrival of radio waves at each antenna, astronomers can reconstruct images with resolution far superior to what any single telescope could achieve. This imaging capability is crucial for SETI research because it allows astronomers to pinpoint exactly where unusual signals are coming from. A radio transmission from an alien civilization would appear as a point source, while natural astrophysical phenomena often have extended structure visible in high-resolution images. The ability to determine whether a signal comes from a specific star or from empty space between stars could be decisive in confirming its artificial origin. The challenge of processing all this data has pushed radio astronomy to the forefront of high-performance computing. A single observation with a modern radio telescope can generate terabytes of data per hour. FAST, operating at full capacity, produces data rates that would overwhelm most computer systems. The raw data stream must be processed in real time, searching for interesting signals while simultaneously storing selected portions for later analysis. This data processing challenge has led to the development of specialized computing systems designed specifically for radio astronomy. These machines use arrays of graphics processing units, originally designed for video games, to perform the millions of calculations per second required to search radio data for artificial signals. The algorithms running on these systems can simultaneously search for dozens of different types of signals, from narrowband continuous wave transmissions to brief pulsed emissions that last only microseconds. The signal-to-noise ratio problem remains fundamental regardless of telescope size. Even the most sensitive radio telescope ever built must distinguish artificial signals from natural background noise. This challenge has led to increasingly sophisticated statistical techniques for separating real signals from random fluctuations in the data. Radio astronomers use a variety of methods to improve signal-to-noise ratios. They integrate observations over long periods, allowing weak signals to accumulate while random noise averages out. They observe the same source multiple times to confirm that unusual signals persist, rather than appearing randomly. They use multiple telescopes simultaneously to verify that signals come from space, rather than from terrestrial interference. But perhaps the most important technique for dealing with cosmic noise is understanding it well enough to subtract it from observations. Modern radio telescopes spend considerable time mapping the natural radio emission from our own galaxy, from nearby radio sources, and from the cosmic microwave background. These maps allow astronomers to predict what the background noise should look like in any direction, making it easier to identify signals that don't fit the expected pattern. The Breakthrough Listen project, launched in 2015, represents the most comprehensive SETI survey ever attempted. Using telescopes including the Green Bank Observatory in West Virginia and the Parkes Observatory in Australia, Breakthrough. Listen monitors millions of nearby stars across frequency ranges spanning several octaves of the radio spectrum. The project's observing strategy reflects decades of lessons learned about the cosmic noise problem. Rather than searching for signals in isolation, Breakthrough Listen observes target stars along with nearby comparison regions of empty sky. Any signal that appears only when pointed at a star and disappears when observing nearby empty space becomes a candidate for further investigation. Breakthrough Listen also employs multiple telescopes simultaneously whenever possible. A true extraterrestrial signal should be detectable by any sufficiently sensitive radio telescope pointed in the right direction, while terrestrial interference typically affects only one telescope at a time. This requirement for simultaneous detection by multiple instruments dramatically reduces the false alarm rate. The project processes its observations using some of the most powerful computing systems ever dedicated to SETI research. The data analysis pipeline can search for millions of different signal types simultaneously, from narrowband beacons to complex modulated transmissions that might carry information. Machine learning algorithms trained on millions of known radio sources help automatically classify detections, flagging the most interesting candidates for detailed human review. Even with these advanced techniques, the fundamental challenge remains daunting. The sensitivity required to detect alien signals depends critically on assumptions about how powerful those signals might be and how they might be transmitted. A civilization broadcasting with the power of a typical terrestrial television transmitter would be undetectable beyond a few light years with current technology. Only signals specifically designed for interstellar communication, using power levels far exceeding anything humans routinely employ, would be detectable across the tens or hundreds of light years to nearby star systems. This realization has led some SETI researchers to focus on detecting the most powerful radio transmitters that alien civilizations might plausibly build. A radio beacon powered by an entire star's energy output, for instance, would be detectable across thousands of light years. Such a beacon would serve as an unmistakable calling card, announcing the presence of a technologically advanced civilization to anyone capable of building sensitive radio telescopes. But even searches for such powerful beacons face the cosmic noise problem. A star-powered radio transmitter would still have to compete with natural radio sources like quasars and radio galaxies that can outshine entire stellar systems. The signal would have to be designed specifically to stand out against the natural radio background, perhaps using artificial characteristics that no known astrophysical process could produce. The evolution of radio telescope technology continues to push the boundaries of what's possible in SETI research. The next generation of radio telescopes promises even greater sensitivity and more sophisticated data processing capabilities. The Square Kilometre Array, currently under construction in South Africa and Australia, will eventually have a collecting area of 1 full square kilometre, making it 50 times more sensitive than any existing radio telescope. SKA will be capable of detecting alien radio transmissions across much greater distances than current telescopes, potentially extending SETI searches to millions of nearby star systems rather than the thousands that current surveys can effectively monitor. Its unprecedented sensitivity might finally allow astronomers to detect the radio leakage from alien civilizations, the unintentional radio emissions that any technological society produces as a byproduct of its communications infrastructure. But increased sensitivity brings its own challenges. More sensitive telescopes detect more signals, including more natural astrophysical sources and more terrestrial interference. The data processing requirements scale exponentially with telescope sensitivity, demanding ever more powerful computing systems and more sophisticated algorithms for signal classification. The cosmic noise problem that motivated the construction of these giant radio telescopes remains as challenging as ever. Every increase in sensitivity reveals new layers of complexity in the natural radio environment. Every new discovery in astrophysics introduces new potential sources of confusion for SETI researchers. the universe continues to surprise us with exotic phenomena that can mimic artificial signals, from fast radio bursts to magnetoflares to the radio emission from exoplanets. Yet these same discoveries also provide new opportunities for understanding how alien signals might hide in the cosmic noise. As astronomers map the natural radio environment in ever greater detail, they create the baseline knowledge necessary to identify anything truly anomalous. The giant radio telescopes that humanity has built to listen for alien signals are simultaneously teaching us about the cosmic environment those signals would have to navigate. In this ongoing competition between technological capability and natural complexity, the next breakthrough might come not from building even larger telescopes, but from developing better techniques for extracting meaningful patterns from overwhelming noise. The whispers from alien civilizations might already be hidden in the data we've collected. We just need to learn how to hear them. In the summer of 1977, Jerry Ayman was doing what radio astronomers do most of the time. Sitting in a cramped office, surrounded by computer printouts, he was methodically analyzing data from the Big Ear radio telescope at Ohio State University. The printouts showed columns of numbers and letters representing signal strength at different frequencies, a seemingly endless stream of cosmic static translated into alphanumeric code. Most of the entries were unremarkable. The letters A through Z represented different levels of background noise, with A indicating no signal above the baseline and higher letters showing stronger detections. On this particular printout, dated August 15th, 1977, most entries clustered around the letters B through F, typical for cosmic background radiation and distant radio sources. Then Ayman saw something that made him grab a red pen. In the middle of an otherwise ordinary column of data, a sequence jumped out at him: 6UQ1. The letter sequence represented a signal more than 30 times stronger than the background noise, concentrated in an incredibly narrow frequency band centered at 1420 megahertz, right in the middle of the protected radio astronomy band, where terrestrial transmitters are prohibited. Ayman circled the anomalous sequence and wrote a single word in the margin: wow. The wow signal, as it came to be known, represents everything tantalizing and frustrating about SETI research. Here was a detection that seemed to check every box for an artificial signal. It appeared at the hydrogen line frequency, where SETI researchers expected to find alien transmissions. It was extremely narrow in bandwidth, unlike the broad-spectrum emissions typical of natural radio sources. It lasted exactly 72 seconds, precisely the time it would take a fixed radio telescope to scan across a point source as Earth rotated. Most intriguingly, the signal appeared to come from the direction of the constellation Sagittarius, from a region of sky where no known stars, planets, or other obvious radio sources existed within reasonable distance of Earth. If the signal originated beyond our solar system, as its characteristics suggested, it would have required enormous power to be detectable across interstellar distances. But the WOW signal has never been detected again. Despite dozens of follow-up observations using more sensitive equipment, no telescope has found any trace of the mysterious transmission. It exists as a single data point in the vast archive of radio astronomy observations, neither confirmed nor convincingly explained away. This is the central challenge of SETI research. Every promising detection eventually falls into the category of what researchers privately call the great cosmic maybes. These are signals that could be artificial or could be natural phenomena we don't yet understand, or could be instrumental glitches that somehow evaded all the safeguards designed to prevent false detections. The WOW signal exemplifies this ambiguity. Over the decades since its discovery, astronomers have proposed numerous possible explanations. It might have been a reflection of Earth-based radar off space debris, or an artificial satellite. It could have been a brief flare from a distant astronomical object, perhaps a magnetar or some other exotic source. Some researchers have even suggested it might have been the radio signature of a comet passing through the telescope's field of view, though this explanation requires the comet to have unusual properties not seen in other cometary observations. Each proposed explanation has problems. Earth-based radar reflections typically show different characteristics than what the WOW signal displayed. Known astronomical phenomena don't easily account for such a narrow band signal appearing only once. Even the comet hypothesis requires assuming that comets can produce coherent radio emission under specific circumstances that aren't well understood. The result is an ongoing debate that illustrates a fundamental problem in SETI research. Without the ability to detect a signal multiple times, or to observe it with multiple telescopes simultaneously, it becomes nearly impossible to definitively classify any detection as artificial or natural. The universe is so vast and so poorly understood that there's almost always a plausible astrophysical explanation for even the most unusual radio signals. This challenge has become even more apparent with the advent of more sensitive detection systems. The Breakthrough Listen project, which began systematic observations in 2015, has detected thousands of candidate signals that initially appeared promising. These detections include narrow band signals that persist for minutes or hours, signals that show apparent Doppler shifts consistent with transmission from orbiting planets, and signals that appear at frequencies where natural emission would be unexpected. Yet every single candidate detected by Breakthrough Listen has eventually been classified as either terrestrial interference or a natural astrophysical source. The project's rigorous follow-up protocols, which require candidate signals to be detected multiple times and to pass a series of increasingly stringent tests, have eliminated each apparent detection as researchers gathered more data. Some candidates have proven particularly stubborn. In 2019, Breakthrough Listen detected a signal designated BLC1 that appeared to come from Proxima Centauri, the nearest star to our solar system. The signal showed characteristics that initially seemed promising for SETI researchers. It was detected over multiple observing sessions, appeared only when the telescope was pointed at Proxima Centauri, and showed a frequency drift that could be consistent with transmission from a planet orbiting the star. BLC1 generated considerable excitement within the SETI community, not because anyone immediately concluded it was artificial, but because it represented the kind of candidate that researchers hoped to find. Here was a signal that couldn't be immediately dismissed, that warranted careful investigation, using multiple telescopes and observing techniques. The follow-up observations ultimately revealed BLC1 to be terrestrial interference, most likely from electronic equipment in the vicinity of the park's observatory, where it was first detected. The signal's apparent association with Proxima Centauri turned out to be coincidental, and its frequency characteristics matched those expected from human technology rather than exotic astrophysical processes. But the BLC1 episode illustrates both the promise and the challenges of modern SETI research. Current detection systems are sensitive enough to identify signals that require weeks or months of careful analysis to fully understand. The false alarm rate for interesting candidates has actually increased as telescopes have become more sensitive, simply because more sensitive instruments detect more signals of all types. This leads to an interesting paradox in SETI research. The better our instruments become at detecting weak signals, the more false alarms they generate, and the more difficult it becomes to identify truly anomalous detections. Every increase in sensitivity reveals new layers of terrestrial interference, new types of natural astrophysical signals, and new instrumental effects that can mimic the characteristics of artificial transmissions. The situation becomes even more complex when considering fast radio bursts, which have emerged as one of the most intriguing phenomena in modern radio astronomy. These millisecond duration flashes of radio energy, first discovered in archival data from 2007, exhibit characteristics so unusual that they briefly sparked speculation about possible artificial origins. FRBs are extraordinary by almost any measure. They release as much energy in a few milliseconds as our Sun produces over several days. They appear to originate from cosmological distances, yet their emission is so precisely timed that it seems almost engineered. Some FRBs repeat at irregular intervals, while others appear only once and never again. The artificial hypothesis for FRBs was never taken seriously by most astronomers, but the phenomenon illustrates how the universe regularly produces radio signals that challenge our understanding of astrophysics. If natural processes can generate something as exotic as FRBs, what other unusual radio phenomena might be lurking in the data, waiting to confuse SETI researchers? Recent discoveries have revealed that FRBs come in multiple varieties with different characteristics. Some originate from highly magnetized neutron stars in our own galaxy, while others appear to come from distant galaxies, billions of light-years away. Some show complex internal structure when observed with sufficient time resolution, while others appear as simple, brief flashes. This diversity has important implications for SETI research. It suggests that the radio universe contains phenomena that we're only beginning to understand. Natural processes that can produce signals with characteristics that might initially appear artificial. Any comprehensive SETI program must account for the possibility that unusual detections might represent new types of astrophysical sources rather than evidence of alien technology. The challenge is compounded by our limited understanding of how alien signals might actually appear. SETI researchers typically search for signals that human engineers might design, transmissions that use terrestrial broadcasting techniques scaled up for interstellar communication. But there's no guarantee that alien civilizations would use radio technology in ways that seem familiar to us. An advanced alien civilization might employ signal processing techniques that we haven't yet developed, or might use modulation schemes that we wouldn't recognize as artificial. They might deliberately design their transmissions to mimic natural astrophysical phenomena, hiding their communications in plain sight among the cosmic radio sources that dominate the spectrum. This possibility has led some researchers to argue for broader approaches to SETI that don't rely on preconceived notions about what alien signals should look like. Instead of searching for specific types of transmissions, these approaches look for any radio phenomena that appear anomalous when compared to our understanding of natural astrophysical processes. The challenge with this strategy is that our understanding of astrophysics is constantly evolving. Phenomena that appear anomalous today might have perfectly natural explanations tomorrow, as astronomers develop better theoretical models and gather more observational data. The history of astronomy is filled with discoveries that initially seemed to require exotic explanations, but were eventually understood in terms of conventional physics. Pulsars themselves provide a perfect example. When Jocelyn Bell first detected these precisely timed radio sources in 1967, they seemed so artificial that she and her colleagues briefly considered the possibility that they were alien beacons. The signals were far more regular than anything known in astronomy, appearing with clockwork precision that seemed to require intelligent control. Only after detecting multiple pulsars with different periods and characteristics did astronomers realize they were observing rapidly rotating neutron stars, objects so dense and compact that they could maintain precise rotation rates for millions of years. What initially appeared artificial turned out to be a natural consequence of stellar evolution under extreme conditions. This pattern has repeated throughout the history of radio astronomy. Unusual signals that initially sparked speculation about possible artificial origins have invariably been explained by natural astrophysical processes, often leading to important discoveries about the universe in the process. The challenge for SETI researchers is distinguishing between signals that represent new astrophysics and those that might actually be artificial. Modern SETI programs have developed sophisticated protocols for handling candidate detections that attempt to minimize both false positives and false negatives. These protocols typically require multiple independent confirmations before any signal can be considered a serious candidate for artificial origin. They involve observations with different telescopes at different times and using different observing techniques to verify that candidates represent genuine astrophysical phenomena rather than instrumental artifacts. The protocols also incorporate what researchers have learned from decades of false alarms. They specifically test for characteristics that distinguish natural astrophysical sources from potential artificial signals, such as polarization properties, spectral characteristics, and temporal behavior. They require candidate signals to persist over multiple observing sessions and to show properties that can't be easily explained by known types of cosmic radio sources. But even with these rigorous verification procedures, the fundamental challenge remains. The universe is so vast and so poorly understood that it's almost impossible to completely rule out natural explanations for unusual radio signals. There's always the possibility that a detection represents some exotic astrophysical phenomenon that we haven't yet discovered or understood. This uncertainty is both the greatest challenge and the greatest opportunity in SETI research. The same cosmic complexity that makes it difficult to identify artificial signals also provides countless opportunities for alien civilizations to hide their communications among natural radio sources. A sufficiently advanced civilization might deliberately exploit our incomplete understanding of astrophysics, designing their transmissions to look exactly like phenomena we already observe but don't fully comprehend. The great cosmic maybes continue to accumulate in the files of radio observatories around the world. Each represents a moment when the universe presented something unexpected, something that doesn't quite fit our current understanding of natural radio sources. Most will eventually be explained by conventional astrophysics, adding to our knowledge of cosmic phenomena while eliminating another potential SETI candidate. But somewhere in that growing archive of anomalous detections, there might be a signal that resists all attempts at natural explanation. A transmission that maintains its artificial characteristics despite increasingly detailed analysis that passes every test designed to distinguish natural from artificial sources. The challenge for SETI researchers is developing the tools and techniques necessary to recognize such a signal when it finally appears among all the cosmic noise. Imagine you're an alien civilization that has mastered interstellar communication, but discovered that the galaxy is not a friendly place. Perhaps you've detected evidence of aggressive species that respond to radio signals by launching devastating attacks on their sources. Or maybe you've learned that broadcasting powerful beacons into space is like lighting a bonfire in a dark forest, attracting unwanted attention from entities you'd rather avoid. How would you communicate across the vast distances between stars without advertising your presence to potentially hostile neighbors? The answer might lie in a technique as old as human civilization itself: steganography, the art of hiding messages in plain sight. On Earth, steganography has taken countless forms throughout history. Ancient Greeks wrote messages on wooden tablets, then covered them with wax bearing innocent text. During World War II, resistance fighters hid coded messages in seemingly harmless letters to relatives. In the digital age, steganography involves hiding data within image files, music tracks, or video streams, embedding secret communications in ordinary-looking digital media. The cosmic equivalent of steganography would involve hiding artificial signals within the natural radio environment of space, making alien transmissions look exactly like the astronomical phenomena that already fill the electromagnetic spectrum. Instead of broadcasting obvious beacons that announce their artificial nature, a sophisticated civilization might design their communications to mimic pulsars, quasars, or other well-known cosmic radio sources. This possibility represents a fundamental shift in how we think about SETI research. For decades, astronomers have searched for signals that stand out against the cosmic background, transmissions that are obviously artificial and clearly distinguishable from natural radio sources. But if alien civilizations are deliberately trying to hide their communications, they might be using the cosmic noise as camouflage rather than trying to overcome it. Consider how such a system might work. A civilization wanting to communicate with distant colonies or trading partners could modulate their messages onto signals that appear to be naturally occurring astronomical phenomena. They might embed data in the timing variations of artificial pulsars, hide information in the frequency structure of synthetic fast radio bursts, or encode messages in radio sources that mimic the characteristics of distant galaxies. The beauty of this approach is that it would be nearly invisible to casual observation. A radio telescope scanning the sky would detect what appeared to be ordinary cosmic radio sources, displaying all the characteristics that astronomers associate with natural astrophysical phenomena. Only someone who knew exactly what to look for and had access to sophisticated analysis techniques would be able to extract the hidden messages from the apparent noise. Such steganographic techniques could explain why SETI searches have been unsuccessful despite decades of increasingly sensitive observations. If alien communications are designed to look like cosmic background noise, they might already be present in the data that radio telescopes collect every day. We could be swimming in alien signals without realizing it, simply because we're looking for the wrong type of transmissions. The technical challenges of implementing cosmic steganography would be enormous, but not necessarily beyond the capabilities of a sufficiently advanced civilization. Modern human technology already demonstrates many of the required techniques on a terrestrial scale. Spread spectrum communications, for instance, deliberately spread signals across wide frequency ranges to make them difficult to detect and jam. Software-defined radios can generate complex waveforms that mimic almost any type of signal, from conventional broadcasts to exotic modulation schemes that don't exist in nature. An alien civilization with thousands or millions of years of technological development could presumably create radio transmissions with any desired characteristics. They could generate artificial pulsars with timing precision that exceeds natural neutron stars, create synthetic fast radio bursts with embedded data, or produce radio sources that perfectly mimic the spectral characteristics of distant quasars while carrying encoded information. The key insight is that any signal that can be detected by radio telescopes can potentially be artificially generated, given sufficient technological sophistication. If natural cosmic phenomena can produce radio emissions with specific timing, frequency, and polarization characteristics, then artificial transmitters could presumably duplicate those same characteristics while adding hidden layers of information. This possibility has profound implications for how we interpret astronomical observations. Every time radio astronomers discover a new type of cosmic radio source, they might actually be detecting either a natural phenomenon or an artificial transmission designed to look natural. Without detailed analysis specifically aimed at detecting hidden information, it would be impossible to tell the difference. The challenge becomes even more complex when you consider that our understanding of natural astrophysical processes is incomplete. We're still discovering new types of cosmic radio sources, from fast radio bursts to rotating radio transients to highly polarized signals from magnetized neutron stars. Each new discovery adds to the catalog of natural phenomena that alien civilizations could potentially mimic. Some researchers have begun to explore what cosmic steganography might look like in practice. They've analyzed known astronomical radio sources to see if any show subtle anomalies that might indicate artificial origin. They've looked for statistical patterns in pulsar timing data that might reveal hidden messages. They've searched for correlations between different types of radio sources that might indicate coordinated artificial signals. So far, these searches have found no convincing evidence of hidden alien communications, but the techniques for detecting cosmic steganography are still in their infancy, and it's possible that we simply haven't developed the right analytical tools to recognize artificial signals embedded in natural-looking transmissions. The detectability of steganographic signals depends critically on how much information the aliens are trying to hide and how much they're willing to distort the natural characteristics of their chosen cover signals. A civilization that needs to transmit large amounts of data might be forced to introduce detectable anomalies into their artificial radio sources. But one that only needs to send occasional brief messages might be able to hide them so subtly that they're effectively undetectable with current technology. Consider a hypothetical alien communication system based on artificial pulsars. Natural pulsars are among the most precisely timed objects in the universe, with rotation periods that can be measured to 15 decimal places. But even natural pulsars show tiny variations in their timing, caused by processes in their magnetospheres and interactions with surrounding material. An artificial pulsar designed for steganographic communication could hide data in these timing variations, encoding information in deviations from perfect periodicity that would look exactly like natural pulsar glitches and timing noise. The data rates would be extremely low by human standards, perhaps only a few bits per day, but the communications would be virtually undetectable without knowing exactly what to look for. Similarly, fast radio bursts could serve as vehicles for hidden information. These brief, intense radio flashes show complex internal structure when observed with sufficient time resolution, including multiple components separated by microseconds and frequency-dependent arrival times that might encode data. An artificial FRB could carry significant amounts of information in its detailed structure while appearing completely natural to conventional analysis. The frequency domain offers another avenue for steganographic communication. Natural astronomical radio sources typically show smooth spectral characteristics, with emission that varies gradually across different frequencies. But within these smooth spectra, there might be room to hide information in subtle spectral features that mimic the effects of interstellar propagation or instrumental response. A steganographic signal could embed data in artificial spectral lines that look like natural atomic or molecular transitions, or in frequency-dependent polarization that appears to result from magnetic fields in interstellar space. The information density would be low, but the signals would be completely camouflaged among the natural spectral features that radio astronomers observe in cosmic sources. Even the apparent randomness of cosmic radio noise could potentially hide information. What we interpret as thermal noise from hot gas clouds or synchrotron emission from high-energy particles might actually contain encoded data, hidden in statistical patterns too subtle for current analysis techniques to detect. The key insight is that randomness and information are closely related concepts. A truly random signal contains maximum information content, but extracting specific messages requires knowledge of the encoding scheme used. An alien civilization could potentially hide vast amounts of data in apparently random cosmic radio emission, using encryption and error correction techniques to ensure reliable communication despite the noisy environment. This possibility raises uncomfortable questions about the nature of astronomical observations. How much of what we interpret as natural cosmic phenomena might actually be artificial? Are we surrounded by alien communications that we mistake for astrophysical processes? Do our radio telescopes regularly detect artificial signals that we automatically classify as natural sources? The answers to these questions depend partly on how common intelligent civilizations are in the galaxy and how often they choose to use steganographic communication techniques. If technological species are rare, then most cosmic radio sources are probably natural. But if the galaxy teems with advanced civilizations that have learned to hide their communications, then artificial signals might be common among the radio sources that astronomers study every day. The steganographic hypothesis also depends on assumptions about alien motivations and capabilities. Why would advanced civilizations choose to hide their communications rather than broadcast openly? The most obvious answer is security, avoiding detection by potentially hostile neighbors. But there might be other reasons, from cultural preferences for privacy to regulations imposed by galactic governing bodies. The technical requirements for cosmic steganography, while challenging, don't seem to exceed what a civilization with advanced technology might achieve. Human engineers are already capable of generating radio signals with arbitrary characteristics, and our pattern recognition abilities continue to improve as machine learning techniques become more sophisticated. A civilization with millions of years of additional development could presumably create steganographic systems of extraordinary subtlety. But implementing such systems would require detailed knowledge of how natural astrophysical processes work and how radio signals propagate through interstellar space. The aliens would need to understand pulsar physics well enough to create convincing artificial pulsars, or comprehend the mechanisms behind fast radio bursts well enough to generate synthetic versions. This requirement might actually provide a way to detect cosmic steganography. If alien civilizations are mimicking natural phenomena they don't fully understand, they might introduce subtle errors or anomalies that betray the artificial nature of their signals. A fake pulsar might show timing characteristics that don't quite match what neutron star physics predicts, or an artificial fast radio burst might have spectral features that don't occur in natural examples. Searching for such anomalies would require incredibly detailed knowledge of astrophysical processes, perhaps more detailed than our current understanding allows. But as our theoretical models improve and our observational capabilities advance, we might eventually be able to distinguish between natural cosmic phenomena and even very sophisticated artificial imitations. The possibility of cosmic steganography adds a new dimension to SETI research, suggesting that alien signals might already be hiding in the vast archives of radio astronomy data. Every pulsar timing measurement, every spectral observation of a distant galaxy, every map of cosmic background radiation might potentially contain hidden messages from alien civilizations. Detecting these hidden signals would require developing new analysis techniques specifically designed to recognize artificial patterns embedded in natural-looking data. It would require understanding natural astrophysical processes well enough to identify subtle deviations that might indicate artificial origin. And it would require accepting that the universe might be far stranger and more populated than our current observations suggest. The search for steganographic alien signals represents one of the most challenging frontiers in SETI research, requiring advances in both observational astronomy and information theory. But it also offers the tantalizing possibility that we might already possess the data needed to confirm the existence of alien civilizations, if only we knew how to read the hidden messages scattered throughout the cosmic noise. In a nondescript server room at the University of California, Berkeley, thousands of computer processors work around the clock on one of the most ambitious pattern recognition projects ever attempted. The machines are sifting through petabytes of radio telescope data, searching for artificial patterns hidden among billions of cosmic signals. They represent humanity's latest weapon in the war against cosmic noise. Algorithms trained to recognize the subtle signatures that might distinguish alien technology from natural astrophysical phenomena. This is the new frontier of SETI research, where artificial intelligence meets radio astronomy in an attempt to find needles in a haystack the size of the observable universe. The challenge is staggering in its complexity. A single hour of observation with a modern radio telescope can generate more data than the entire written history of human civilization. Hidden somewhere in that overwhelming flood of information might be signals from alien civilizations, patterns too subtle or complex for human researchers to detect manually. The scale of the pattern recognition problem in SETI is unlike anything else in science. Traditional radio astronomy involves searching for known types of signals, cosmic phenomena that astronomers understand well enough to recognize when they appear in data. But SETI researchers are looking for something unprecedented, signals that might use technologies and modulation schemes completely foreign to human experience. Consider the challenge facing a computer algorithm tasked with distinguishing artificial signals from natural cosmic radio sources. The algorithm must process millions of frequency channels simultaneously, looking for patterns that might indicate intelligence while avoiding false alarms from the countless astrophysical phenomena that can mimic artificial signals. It must be sensitive enough to detect incredibly weak transmissions, yet robust enough to ignore the constant barrage of terrestrial interference that contaminates radio observations. Modern SETI algorithms use machine learning techniques borrowed from fields as diverse as computer vision, natural language processing, and financial analysis. These systems learn to recognize patterns by training on vast datasets of known signals, gradually developing the ability to distinguish between different types of radio emissions based on their statistical characteristics. The training process involves exposing the algorithms to millions of examples of both natural and artificial signals. Natural examples include pulsars, quasars, thermal emission from gas clouds, and all the other cosmic radio sources that fill the electromagnetic spectrum. Artificial examples include terrestrial radio transmissions, radar signals, and synthetic signals designed to test the algorithm's detection capabilities. But this training process faces a fundamental problem unique to SETI research. Unlike other pattern recognition applications, there are no confirmed examples of alien signals to use as training data. The algorithms must learn to recognize artificial patterns based entirely on human-made signals and theoretical models of what alien transmissions might look like. This creates a potential bias in SETI pattern recognition systems. They're essentially trained to find signals that look like human technology, scaled up for interstellar communication. But there's no guarantee that alien civilizations would use modulation schemes, frequency choices, or signal structures that seem familiar to human engineers. Advanced machine learning techniques are attempting to address this limitation by searching for any signals that appear anomalous compared to known natural phenomena, regardless of whether they match human expectations for artificial transmissions. These systems use unsupervised learning algorithms to identify outliers in the radio data, flagging any signals that don't fit the statistical patterns expected from natural astrophysical sources. The most sophisticated SETI algorithms employ deep neural networks with millions of parameters, trained on datasets containing billions of signal examples. These networks can learn to recognize incredibly subtle patterns in radio data, detecting correlations and structures that would be invisible to human analysis or traditional signal processing techniques. One promising approach involves training neural networks on the time-frequency structure of radio signals. Natural astrophysical phenomena typically show specific patterns in how their emission changes over time and frequency, reflecting the underlying physical processes that generate the radio waves. Artificial signals might show different patterns, particularly if they're designed to carry information or if they use technologies not found in nature. For example, pulsars show extremely regular timing with occasional glitches caused by changes in their internal structure. Quasars can vary dramatically in brightness, but typically show smooth changes that reflect processes in their accretion disks. Artificial signals might show patterns that don't match either of these natural behaviors, revealing their technological origin to sufficiently sophisticated pattern recognition systems. Another approach focuses on the spectral characteristics of radio signals. Natural cosmic radio sources typically show broad, smooth spectra that reflect thermal processes or synchrotron emission from high-energy particles. Artificial signals might show narrow spectral features, complex modulation patterns, or frequency structures that don't occur in natural astrophysical environments. Machine learning algorithms trained on spectral data can learn to recognize these subtle differences, identifying signals that show artificial characteristics, even when they're embedded in much stronger natural emission. The algorithms can simultaneously analyze thousands of spectral features, looking for combinations of characteristics that might indicate technological origin. The challenge becomes even more complex when considering that alien signals might be deliberately designed to evade detection. If extraterrestrial civilizations are using steganographic techniques to hide their communications among natural cosmic radio sources, they might employ sophisticated countermeasures specifically designed to fool pattern recognition systems. This has led to an arms race between detection algorithms and hypothetical alien steganography techniques. SETI researchers develop increasingly sophisticated pattern recognition systems, while simultaneously trying to anticipate how advanced alien civilizations might attempt to hide their signals from such systems. Some researchers have begun exploring adversarial machine learning techniques, originally developed for cybersecurity applications, to model how alien civilizations might try to evade detection. These techniques involve training two neural networks simultaneously, one trying to detect hidden signals and another trying to hide them more effectively. The resulting systems can identify steganographic techniques that might be difficult to detect with conventional algorithms. The computational requirements for modern SETI pattern recognition are enormous. The Breakthrough Listen project alone generates several petabytes of data annually, requiring some of the most powerful computing systems ever dedicated to astronomical research. The data processing pipeline involves thousands of graphics processing units working in parallel, each analyzing different portions of the radio spectrum simultaneously. But even with this massive computational power, the pattern recognition problem remains daunting. The algorithms must search through parameter spaces with hundreds or thousands of dimensions, looking for signals that might use any combination of frequency, timing, polarization, and modulation characteristics. The number of possible signal types is effectively infinite, making exhaustive searches impossible. This has led to the development of adaptive search strategies that can dynamically adjust their parameters based on what they find in the data. Instead of searching for predetermined signal types, these systems learn from the radio environment they're observing, gradually focusing their attention on frequency ranges and signal characteristics that show the most promise. The algorithms also incorporate feedback from human researchers who review the most promising candidates detected by the automated systems. This human-machine collaboration allows the pattern recognition systems to learn from expert knowledge while processing data volumes that would overwhelm purely manual analysis. False positive rates remain a major challenge for SETI pattern recognition systems. The algorithms are designed to be extremely sensitive, capable of detecting signals buried deep in noise and interference. But this sensitivity inevitably leads to large numbers of false alarms, signals that initially appear artificial but turn out to have natural explanations. Modern SETI algorithms address this problem through multi-stage verification processes. Initial detection algorithms identify potential candidates with high sensitivity but limited specificity. These candidates are then subjected to increasingly rigorous tests, using different analysis techniques and observational strategies to confirm or rule out their artificial nature. Machine learning plays a crucial role in this verification process. Classification algorithms trained on millions of known signal types can automatically categorize most detections as terrestrial interference, known astrophysical sources, or instrumental artifacts. Only the small fraction of signals that resist automated classification are flagged for detailed human review. The most advanced SETI pattern recognition systems now incorporate techniques from multiple machine learning disciplines. Computer vision algorithms analyze time-frequency plots of radio data, looking for visual patterns that might indicate artificial origin. Natural language processing techniques search for information theoretic signatures in signal modulation that might reveal embedded data. Statistical learning algorithms identify correlations between different observational parameters that might indicate coordinated artificial transmissions. Some researchers are even exploring quantum machine learning techniques, using quantum computers to search for patterns in radio data that might be impossible to detect with classical algorithms. While still in early stages, these approaches might eventually provide new ways to extract artificial signals from cosmic noise. The pattern recognition challenge is complicated by the fact that radio telescopes themselves introduce artifacts that can mimic artificial signals. Instrumental effects, data processing errors, and interference from electronic equipment can all create patterns in radio data that initially appear anomalous. SATI algorithms must learn to recognize and filter out these false signals while remaining sensitive to genuine anomalies. This requires detailed modeling of telescope characteristics and data processing pipelines. Machine learning algorithms are trained not just on cosmic radio sources, but on the complex ways that radio telescopes interact with their environment. The algorithms learn to recognize the signatures of instrumental effects, allowing them to distinguish between genuine astrophysical signals and artifacts created by the observation process itself. The integration of multiple telescopes into SETI pattern recognition systems provides another layer of verification. Signals that appear on multiple independent telescopes are more likely to be genuine astrophysical phenomena, while signals detected by only one instrument might indicate local interference or instrumental problems. Advanced algorithms can correlate data from multiple telescopes in real time, searching for patterns that appear consistently across different observing sites. This multi-telescope approach dramatically reduces false alarm rates while increasing confidence in genuine detections. The future of SETI pattern recognition lies in even more sophisticated integration of artificial intelligence with radio astronomy. Researchers are developing systems that can learn continuously from new observations, adapting their search strategies as they gather more data about the cosmic radio environment. These adaptive systems might eventually become sophisticated enough to discover new types of natural astrophysical phenomena while simultaneously searching for artificial signals. They could serve dual roles, advancing our understanding of cosmic radio sources while hunting for evidence of alien technology. The ultimate goal is to create pattern recognition systems that are more sensitive and more intelligent than any human researcher, capable of detecting artificial patterns so subtle that they would be invisible to conventional analysis. These systems would need to process data from next-generation radio telescopes that will be orders of magnitude more sensitive than current instruments. But perhaps the most intriguing possibility is that machine learning algorithms might discover patterns in existing radio astronomy data that have been overlooked by human researchers. The archives of radio observatories contain decades of observations, much of which has never been subjected to modern pattern recognition techniques. Hidden somewhere in those vast databases might be artificial signals that were recorded years or decades ago, but never recognized as such. The pattern hunters working to develop new SETI algorithms might not just find alien civilizations in future observations. They might discover that we've already been listening to alien transmissions for years, hidden in plain sight among the cosmic noise that fills our radio telescopes every day. As these algorithms become more sophisticated and more powerful, they're transforming SETI from a search for obvious artificial beacons into a comprehensive analysis of the cosmic radio environment. They're teaching us that intelligence might hide in places we never thought to look, embedded in patterns too complex for human recognition, but perfectly clear to sufficiently advanced artificial minds. Despite all the sophisticated algorithms and artificial intelligence systems deployed in modern SETI research, there remains one element that no amount of computational power can replace: the human mind, with all its remarkable pattern recognition abilities and all its troublesome biases, continues to play a crucial role in the search for extraterrestrial intelligence. And therein lies both the greatest strength and the greatest weakness of the entire enterprise. Human beings are extraordinary pattern recognition machines, evolved over millions of years to detect meaningful signals in noisy environments. Our ancestors, who could spot the subtle signs of predators hiding in tall grass or recognize the faint traces of game trails through dense forest, were more likely to survive and pass on their genes. This evolutionary heritage has left us with brains that are almost supernaturally good at finding patterns, even in random data. But this same ability that served our ancestors so well can become a liability when searching for alien signals in cosmic noise. The human tendency to see patterns where none exist, to impose meaning on random data, and to interpret ambiguous information in ways that confirm our expectations can lead SETI researchers down fascinating but ultimately futile paths. The history of radio astronomy is littered with examples of signals that initially seemed artificial but turned out to have perfectly natural explanations. Each case illustrates how human psychology can influence scientific interpretation, turning mundane astrophysical phenomena into apparent evidence of extraterrestrial intelligence. One of the most dramatic examples occurred in the early 2000s, when radio astronomers began detecting strange signals that seemed to appear randomly during observations at the Parkes Observatory in Australia. The signals, dubbed peritons after creatures from mythology, showed characteristics that didn't match any known type of cosmic radio source. They appeared across wide frequency ranges, lasted for several seconds, and seemed to originate from directions scattered across the sky. For years, peritons remained a genuine mystery. They couldn't be easily explained as terrestrial interference because they showed characteristics similar to cosmic signals. They didn't match the patterns expected from any known type of astrophysical source. Some researchers began to wonder if they might represent a new category of astronomical phenomenon, or even artificial signals from an alien civilization using some exotic communication technology. The truth, when it was finally discovered in 2015, was both embarrassing and enlightening. Peritons were produced by microwave ovens in the observatory's cafeteria and staff areas. When the ovens were opened before their cooking cycles completed, they emitted brief bursts of microwave radiation that the radio telescope detected as mysterious cosmic signals. The Periton episode illustrates how easy it is for human researchers to construct elaborate explanations for mundane phenomena when they don't immediately recognize the true source. The signals showed some characteristics that seemed cosmic in origin, and astronomers naturally tried to fit them into their understanding of astrophysical processes. When conventional explanations failed, more exotic possibilities began to seem plausible. This pattern of interpretation reflects fundamental aspects of human psychology that affect all scientific research, but which become particularly problematic in SETI studies. We have a natural tendency to see intelligence and purpose in patterns, even when those patterns arise from completely random processes. We're inclined to interpret ambiguous data in ways that support our existing beliefs and expectations. And we're often reluctant to abandon interesting hypotheses even when simpler explanations become available. The search for extraterrestrial intelligence is especially vulnerable to these cognitive biases because it deals with phenomena at the very limits of our detection capabilities. SETI researchers are looking for signals so weak and so rare that they're barely distinguishable from noise. In this environment, the difference between a genuine detection and a false alarm often comes down to subjective human judgment about whether an apparent pattern is real or imaginary. Consider the challenge facing a radio astronomer who notices an unusual signal in telescope data. The signal might show characteristics that seem artificial, perhaps appearing at a specific frequency with timing patterns that don't obviously match known natural sources. But the signal might also be weak, brief, or embedded in interference that makes its properties difficult to determine definitively. How should the astronomer interpret this detection? Human psychology pushes toward finding meaning and significance in unusual observations. The natural tendency is to focus on the characteristics that seem most interesting or most consistent with artificial origin, while downplaying aspects that might suggest more mundane explanations. This interpretive bias is compounded by the social dynamics of scientific research. Discovering evidence of extraterrestrial intelligence would be one of the most significant scientific breakthroughs in human history. The researcher who makes such a discovery would achieve instant fame and historical importance. These incentives, even when not consciously acknowledged, can influence how ambiguous data is interpreted and presented. The problem becomes even more complex when multiple researchers become involved in analyzing a potential signal. Group psychology can amplify individual biases, leading teams of scientists to collectively convince themselves that marginal detections are more significant than they really are. The desire to avoid missing a historic discovery can override normal scientific skepticism, particularly when dealing with signals that resist easy classification. Professional SETI researchers are well aware of these psychological pitfalls and have developed protocols specifically designed to minimize their influence. Modern SETI programs incorporate multiple layers of verification, requiring signals to be detected independently by different telescopes and analyzed by different research teams before they can be considered genuine candidates. But even with these safeguards, human interpretation continues to play a crucial role in SETI research. Automated algorithms can process vast amounts of data and flag potential candidates. But human researchers must ultimately decide which signals warrant further investigation and how to interpret ambiguous results. This human element introduces both strengths and weaknesses into the search process. Human researchers bring intuition, creativity, and the ability to recognize patterns that might not be obvious to algorithmic analysis. They can spot subtle anomalies in data that automated systems might miss, and they can develop new analysis techniques when conventional approaches fail to provide clear answers. But human researchers also bring cognitive biases, wishful thinking, and the tendency to see patterns where none exist. They might pursue promising but ultimately incorrect interpretations of data, or overlook simpler explanations for unusual observations in favor of more exotic possibilities. The challenge is particularly acute because SETI research operates in a domain where our intuitions about what constitutes evidence are poorly calibrated. In most scientific fields, researchers have extensive experience with the types of phenomena they study, allowing them to develop reliable instincts about which observations are likely to be significant. But SETI researchers have no confirmed examples of alien signals to guide their interpretations. This lack of confirmed positive examples makes it extremely difficult to distinguish between genuine signals and false alarms. Without knowing what alien transmissions actually look like, how can researchers reliably identify them when they appear in telescope data? The answer, unfortunately, is that they probably can't, at least not with current knowledge and techniques. This fundamental uncertainty means that SETI research is particularly susceptible to confirmation bias, the tendency to interpret ambiguous information in ways that support pre-existing beliefs. Researchers who strongly believe that alien civilizations exist and are broadcasting detectable signals might be inclined to interpret marginal detections as evidence supporting that belief. Conversely, researchers who are skeptical about the existence of detectable alien signals might be too quick to dismiss potentially interesting observations. The history of SETI is filled with examples of both types of bias. Some researchers have championed signals that later proved to have mundane explanations, while others have perhaps been too conservative in their interpretation of unusual detections. The field has had to learn, sometimes painfully, how to balance appropriate skepticism with openness to genuine discoveries. One approach to managing these psychological challenges involves deliberately incorporating contrarian perspectives into SETI research. Some projects now assign specific team members to argue against the artificial origin of potential detections. forcing proponents to address the strongest possible criticisms of their interpretations. This adversarial approach helps counter the natural tendency to focus on evidence that supports preferred conclusions while ignoring contradictory data. Another strategy involves blind analysis techniques, where researchers analyze signals without knowing their source or the circumstances of their detection. This prevents prior knowledge about a signal's origin from influencing the analysis, reducing the risk that researchers will unconsciously bias their interpretation toward or away from artificial explanations. But perhaps the most important safeguard against human bias in SETI research is the requirement for independent confirmation. No signal can be considered a serious candidate for artificial origin unless it can be detected and verified by multiple independent research groups using different telescopes and analysis techniques. This requirement helps ensure that individual or group biases don't lead to false claims of discovery. The reproducibility requirement has proven effective at filtering out false alarms, but it also makes genuine discoveries more difficult to confirm. If alien signals are rare, brief, or deliberately designed to evade detection, they might not be easily reproducible using conventional observational techniques. The requirement for independent confirmation might actually prevent the recognition of genuine alien transmissions that don't conform to our expectations about how such signals should behave. This creates a difficult balance for SETI researchers. They must be skeptical enough to avoid false alarms while remaining open to genuine discoveries that might not fit conventional patterns. They must account for human psychological biases while still trusting human intuition and creativity in developing new search strategies. The solution, if there is one, probably lies in developing better understanding of how human psychology interacts with the search for extraterrestrial intelligence. SETI researchers need to become experts, not just in radio astronomy and signal processing, but in cognitive psychology and the scientific method. They need to understand their own biases and develop techniques for minimizing their influence on data interpretation. This psychological awareness is becoming increasingly important as SETI research becomes more sophisticated and more sensitive. Next-generation radio telescopes will detect far more candidate signals than current instruments, creating even greater challenges for distinguishing genuine anomalies from false alarms. The role of human judgment in evaluating these candidates will become even more critical. But there's also reason for optimism about the human factor in SETI research. As the field matures and gains more experience with different types of signals and false alarms, researchers are developing better intuitions about what constitutes genuine evidence. The lessons learned from peritons, fast radio bursts, and countless other false alarms are helping to calibrate human expectations about what alien signals might actually look like. Perhaps most importantly, the SETI community has developed a culture of healthy skepticism that encourages researchers to question their own interpretations and seek independent verification of unusual observations. This culture, combined with increasingly sophisticated analysis techniques and verification protocols, provides the best available protection against the psychological pitfalls that have plagued the field in the past. The human factor will never be completely eliminated from SETI research, nor should it be. Human creativity, intuition, and pattern recognition abilities remain essential for recognizing truly anomalous signals and developing new search strategies. The challenge is learning to harness these human strengths while minimizing the influence of human weaknesses on the search for extraterrestrial intelligence. In the end, the discovery of alien signals will probably require both sophisticated technology and human insight working together. Machines can process vast amounts of data and identify potential candidates, but humans must ultimately decide what those candidates mean and whether they represent genuine evidence of extraterrestrial intelligence. The key is ensuring that this human interpretation is as objective, rigorous, and free from bias as possible. The cosmic noise that fills our radio telescopes reflects not just the natural electromagnetic environment of the universe, but also the noise of human psychology and the patterns we impose on ambiguous data. Learning to separate genuine signals from both types of noise may be the greatest challenge facing the search for extraterrestrial intelligence. The moment arrives without fanfare, hidden in the routine flow of data from a radio telescope, scanning the sky on an ordinary Tuesday morning. An automated algorithm, one of thousands running continuously on computer clusters around the world, flags an anomaly in the signal from a star 43 light-years away. The detection appears in a priority queue alongside dozens of other potential candidates, most of which will prove to be terrestrial interference or known astrophysical sources. But this signal is different. It persists across multiple observing sessions, shows characteristics that don't match any known natural phenomenon, and appears only when telescopes point toward the target star. After weeks of careful analysis and independent confirmation by multiple observatories, researchers begin to use a phrase they've rehearsed but never spoken in earnest. This might be it. The discovery of humanity's first confirmed alien signal would unfold very differently from the dramatic scenarios portrayed in science fiction. There would be no sudden interruption of television broadcasts, no mysterious messages appearing simultaneously around the world. Instead, the detection would emerge gradually from the cosmic noise, requiring months or years of careful analysis before researchers could be confident of its artificial origin. The process would begin with automated detection systems flagging unusual signals for human review. Modern SETI programs process so much data that human researchers can't possibly examine every potential candidate manually. Machine learning algorithms serve as the first filter, identifying signals that show characteristics potentially consistent with artificial origin, while discarding the vast majority of detections as known interference or natural sources. A genuine alien signal might initially appear unremarkable, perhaps showing up as nothing more than a narrow band emission that persists longer than expected from natural sources. The first indication of its artificial nature might be subtle, a statistical anomaly that suggests the signal contains more structure than random noise should exhibit. The verification process would be methodical and exhaustive. Researchers would need to rule out every possible natural explanation before seriously considering artificial origin. They would examine the signal's frequency characteristics, temporal behavior, polarization properties, and spatial distribution. They would search for correlations with known astrophysical phenomena, solar activity, terrestrial interference, and instrumental effects. Most importantly, they would require independent confirmation from multiple telescopes. A signal detected by only one observatory could easily be a local artifact, no matter how exotic its characteristics appear. True extraterrestrial signals should be detectable by any sufficiently sensitive radio telescope pointed in the right direction, though the exact detection requirements would depend on the signal's strength and characteristics. The independent confirmation process could take months or years to complete. Different telescopes have different sensitivities, frequency ranges, and observing schedules. Coordinating simultaneous observations of potential alien signals would require unprecedented cooperation between observatories that normally operate independently. The logistics alone could delay confirmation significantly. During this verification period, researchers would face enormous pressure to either confirm or dismiss the candidate signal. The possibility of detecting humanity's first alien transmission would generate intense interest from the scientific community, the media, and the general public. But premature announcements could lead to false alarms that would damage the credibility of SETI research for decades. The scientific protocols for handling potential alien signals have been developed over decades of SETI research, refined through experience with false alarms and near misses. These protocols emphasize careful analysis, independent verification, and conservative interpretation of ambiguous data. They're designed to prevent the kind of spectacular false alarms that could discredit the entire field. But the protocols also reflect assumptions about what alien signals might look like and how they should be detected. A signal that doesn't conform to these expectations might not trigger the standard verification procedures, potentially leading to missed discoveries or delayed recognition of genuine transmissions. Consider the challenges that would arise if the first confirmed alien signal turned out to be embedded in cosmic noise using steganographic techniques. Such a signal might not show obvious artificial characteristics, instead appearing as a subtle anomaly in otherwise natural-looking radio emission. Detecting and confirming such a signal would require analysis techniques specifically designed to recognize hidden patterns, which might not be part of standard SETI verification protocols. The international implications of confirming an alien signal would be enormous. The detection would represent one of the most significant discoveries in human history, with profound implications for science, philosophy, religion, and society. The researchers responsible for the discovery would need to coordinate their announcement with government agencies, international organizations, and the broader scientific community. Existing protocols call for notifying the International Astronomical Union and other scientific organizations before making any public announcements. The goal is to ensure that the discovery is properly verified and that the scientific community has time to prepare for the inevitable media attention and public reaction. But these protocols assume that alien signals will be detected by professional CT researchers using established scientific procedures. A signal discovered by amateur radio astronomers, detected through citizen science projects, or identified by artificial intelligence systems might not follow the standard notification pathways. The first confirmed alien signal might be announced on social media or amateur radio networks before professional scientists even know it exists. The content of the alien signal would raise additional challenges for verification and interpretation. A simple beacon containing no obvious information might be easier to confirm as artificial, but would provide little insight into the civilization that created it. A complex signal carrying encoded information might be harder to verify, but could reveal details about alien technology, culture, or intentions. Decoding an information-bearing alien signal would require expertise in cryptography, information theory, and linguistics, disciplines that don't normally intersect with radio astronomy. The analysis might take years or decades, particularly if the aliens use encoding schemes or mathematical concepts unfamiliar to human science. The signal's characteristics could also provide clues about the alien civilization's technology and intentions. A powerful, obvious beacon would suggest a civilization actively trying to communicate with other species. A weak signal hidden in cosmic noise might indicate a more cautious approach, perhaps reflecting concerns about revealing their location to potentially hostile neighbors. The frequency and timing of the signal could reveal information about the aliens' understanding of physics and their technological capabilities. Signals that show evidence of sophisticated error correction, complex modulation schemes, or exotic physics might indicate highly advanced civilizations. Simple, repetitive signals might suggest earlier stages of technological development. But interpreting these characteristics would require careful analysis and probably some educated guesswork. Human researchers would be trying to understand alien technology using theoretical frameworks developed for human engineering. The aliens might use completely different approaches to radio communication, making their signals difficult to interpret even after detection. The location of the signal source would raise additional questions about verification and response. A signal from a nearby star system might allow for more detailed analysis using multiple telescopes and observing techniques. Signals from more distant sources might be harder to study, but would indicate civilizations with much more powerful transmitters. The possibility of multiple signals from different sources would complicate the verification process enormously. If SETI researchers detected several candidate signals simultaneously, they would need to determine whether they represented independent alien civilizations, coordinated transmissions from the same source, or coincidental false alarms. The analysis requirements would scale exponentially with the number of candidates. Even after confirmation, researchers would face difficult decisions about how to respond to the alien signal. Existing SETI protocols discourage unauthorized responses to potential alien transmissions, partly to prevent confusion about who speaks for humanity, and partly to avoid revealing our location to potentially hostile civilizations. But the temptation to respond would be enormous, particularly if the alien signal appeared to be deliberately attempting to establish communication. Amateur radio operators, governments, or other organizations might attempt to transmit responses regardless of official protocols. Controlling or coordinating humanity's response to first contact would require unprecedented international cooperation. The verification of first contact would also raise fundamental questions about the nature of intelligence and communication. How would researchers distinguish between signals from biological civilizations and transmissions from artificial intelligence systems? How would they determine whether detected signals represent current alien activity or ancient transmissions from civilizations that no longer exist? These questions become particularly relevant when considering signals that might have been traveling through space for thousands or millions of years before reaching Earth. The civilization that created the transmission might have evolved, migrated, or gone extinct long before their signal arrived in our solar system. First contact might actually be contact with alien history rather than alien contemporaries. The cosmic noise that has made detecting alien signals so difficult might actually provide advantages during the verification process. Natural radio sources would serve as calibration standards, helping researchers understand how different types of signals propagate through interstellar space and how they're affected by the transmission medium. The same astrophysical knowledge that CT researchers have developed to distinguish artificial signals from cosmic noise would be essential for interpreting confirmed alien transmissions. Understanding how radio waves interact with interstellar gas, magnetic fields, and gravitational effects would be crucial for determining the original characteristics of alien signals and the distances they've traveled. The statistical properties of cosmic noise might also help verify the artificial nature of genuine alien signals. Natural radio sources show specific types of variability and frequency structure that reflect underlying physical processes. Artificial signals would likely show different statistical characteristics, particularly if they're designed to carry information or to stand out against natural background emission. Perhaps most importantly, the process of verification would establish precedents for handling future detections. The first confirmed alien signal would teach researchers about what kinds of verification procedures work effectively, what types of false alarms are most dangerous, and how to balance scientific rigor with public communication needs. The discovery would also provide crucial data for improving SETI search strategies. Understanding what the first confirmed alien signal actually looks like would help researchers develop better detection algorithms, choose more effective target frequencies, and design more sensitive instruments for future searches. But the confirmation of first contact would mark just the beginning of a much longer process of understanding and communication. The initial detection would be followed by decades of detailed analysis, attempts at decoding any information content, and careful monitoring for additional signals from the same source or other locations. The cosmic noise that once obscured alien signals would become a subject of even more intense study, as researchers searched for additional hidden transmissions that might have been overlooked in previous observations. Every anomaly in the vast archives of radio astronomy data would be re-examined with new understanding of what artificial signals actually look like. First contact through radio signals would transform humanity's relationship with the cosmos turning the universe from a seemingly empty wilderness into a neighborhood where other intelligence exists. But it would also be just the first step in a much longer journey toward understanding our place in a galaxy that might be far more crowded and complex than we ever imagined. After more than 60 years of searching, the most striking characteristic of the cosmos is not its noise, but its silence. Despite decades of increasingly sophisticated observations, despite radio telescopes capable of detecting signals from civilizations thousands of light years away, despite algorithms that can process data from millions of star systems simultaneously, we have found no confirmed evidence of extraterrestrial intelligence. The universe appears to be broadcasting at every frequency, filled with natural radio sources of extraordinary power and complexity, yet eerily quiet when it comes to artificial signals. This silence is puzzling for reasons that go far beyond CT research itself. Our galaxy contains several hundred billion stars, many of them older than our Sun, and potentially harboring planetary systems where life could have evolved. Conservative estimates suggest that millions of star systems in the Milky Way might have developed conditions suitable for life at some point in their history. Even if intelligence is extraordinarily rare, the sheer number of opportunities suggests that we should not be alone. This contradiction between the apparent abundance of potentially habitable worlds and the absence of detected alien signals has become known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The question has profound implications for our understanding of life, intelligence, and our place in the universe. The silence becomes even more puzzling when you consider how easy it should be for advanced civilizations to make their presence known across galactic distances. A radio transmitter powered by a star's entire energy output would be detectable by current Earth technology from anywhere in the galaxy. Even more modest transmissions using power levels comparable to our largest military radars would be detectable across hundreds of light years. If alien civilizations wanted to announce their presence, they could easily do so using technology not much more advanced than our own. The fact that we haven't detected such obvious beacons suggests either that intelligence is far rarer than we expect, or that advanced civilizations choose not to broadcast their existence across interstellar distances. This latter possibility, that aliens are deliberately hiding, has become increasingly plausible as we've learned more about the potential dangers of advertising one's presence in an uncertain galaxy. If the cosmos contains aggressive species that respond to radio signals by attacking their sources, then broadcasting powerful beacons might be tantamount to suicide. Natural selection would favor civilizations that learn to communicate quietly, avoiding the attention of hostile neighbors. The concept of a dark forest universe where civilizations remain hidden out of fear of each other provides one possible explanation for the cosmic silence. In this scenario, the galaxy might be teeming with intelligent species, all of them maintaining strict radio silence to avoid revealing their locations to potential predators. Any civilization that broadcasts openly would quickly be eliminated, leaving only the quiet ones to survive and reproduce. This hypothesis suggests that the absence of obvious alien beacons doesn't necessarily mean we're alone. Instead, it might indicate that we're living in a universe where intelligence has learned to be circumspect, where survival depends on remaining undetected by other technological species. If this interpretation is correct, then searching for alien signals in cosmic noise might be exactly the right approach. Hidden civilizations might use steganographic techniques to embed their communications in natural-looking radio emission, disguising their transmissions as pulsars, quasars, or other cosmic phenomena. The signals we're looking for might already be present in our data, camouflaged so effectively that we mistake them for natural astrophysical sources. But the dark forest hypothesis raises troubling questions about humanity's own radio emissions. For more than a century, we've been inadvertently announcing our presence to the galaxy through radio and television broadcasts. military radar signals, and other electromagnetic emissions. These unintentional transmissions, collectively known as radio leakage, have created an expanding sphere of detectability around Earth that now extends more than 100 light-years into space. Any civilization within this sphere, equipped with sufficiently sensitive radio telescopes, could potentially detect evidence of human technology. If the galaxy really does contain aggressive species that attack the sources of radio signals, then we might have already painted a target on ourselves that will become visible to hostile aliens in the coming centuries. The possibility that we're being watched by hidden alien civilizations, waiting to see how we develop before revealing themselves, adds another dimension to the cosmic silence. Perhaps the galaxy operates under a kind of prime directive, where advanced species avoid interfering with younger civilizations until they reach certain technological or ethical milestones. In this scenario, the absence of detected alien signals might reflect a deliberate policy of non-interference rather than genuine absence of intelligence. The aliens might be there, observing our development through telescopes and radio receivers far more sophisticated than our own, but remaining silent until we demonstrate our readiness for contact. Such a policy would make sense from the perspective of advanced civilizations that have witnessed the rise and fall of countless younger species. Premature contact might disrupt natural development patterns, preventing emerging civilizations from developing the wisdom and maturity necessary to handle advanced technology responsibly. The cosmic silence might also reflect the simple fact that interstellar communication is far more difficult than early SETI researchers anticipated. While it's theoretically possible to build transmitters powerful enough to communicate across galactic distances, the energy requirements are enormous, and the information transfer rates would be frustratingly slow. A signal traveling from a star system 100 light-years away would take 100 years to reach Earth, and any response we sent would take another 100 years to return. This 4-century round-trip time would make meaningful conversation impossible, limiting interstellar communication to the transmission of basic information like mathematical concepts, scientific data, or cultural artifacts. Such extreme communication delays might discourage most civilizations from attempting interstellar broadcasting, particularly if they have other priorities for their energy resources. It might be more efficient to focus on local development, expansion within their own solar systems, or communication with nearby neighbors rather than trying to establish contact across the vast distances between stars. The silence might also reflect technological choices that we haven't anticipated. Human SETI efforts focus primarily on radio communications because that's the technology we understand best, and because radio waves can travel long distances through interstellar space with relatively little attenuation. But advanced civilizations might use completely different communication methods that we haven't learned to detect. Optical laser communication, for instance, can achieve much higher data rates than radio transmission and might be less susceptible to interference from cosmic noise. But laser signals would be extremely difficult to detect unless we happen to be directly in their beam path, and they would require precise targeting systems that could account for the motion of both transmitter and receiver over interstellar distances. Even more exotic communication methods might use gravitational waves, neutrino beams, or quantum entanglement effects that we're only beginning to understand. An alien civilization using such technologies might be completely invisible to our current detection methods, no matter how powerful their transmissions might be. The possibility that aliens have moved beyond radio communication entirely could explain why SETI searches have been unsuccessful despite decades of increasingly sophisticated observations. We might be looking for the cosmic equivalent of smoke signals, while advanced civilizations have moved on to technologies as far beyond radio as the internet is beyond telegraph systems. Another explanation for the cosmic silence involves the temporal mismatch between the development of intelligence and the lifetime of technological civilizations. If most intelligent species destroy themselves shortly after developing advanced technology, then there might be very few civilizations broadcasting at any given time, even if intelligence has evolved many times throughout galactic history. The nuclear weapons that humanity developed within decades of mastering radio technology illustrate how quickly advanced knowledge can create existential risks. Climate change, artificial intelligence, biotechnology, and other emerging technologies present additional challenges that could determine whether our civilization survives its technological adolescence. If most species face similar challenges and most fail to overcome them, then the galaxy might be filled with the ruins of dead civilizations rather than active technological societies. The cosmic silence might reflect not the absence of intelligence, but the difficulty of maintaining technological civilization for extended periods. This interpretation suggests that SETI researchers might occasionally detect signals from civilizations that no longer exist, ancient transmissions that have been traveling through space for thousands or millions of years since their creators went extinct. Such archaeological signals would provide evidence that intelligence had existed elsewhere in the galaxy, but wouldn't indicate the presence of contemporary alien civilizations. The search for extraterrestrial intelligence might thus be as much about understanding the fate of technological civilizations as about establishing communication with alien species. Every detection or non-detection provides data about how common intelligence is, how long technological civilizations survive, and what factors determine their success or failure. But perhaps the most unsettling possibility is that the cosmic silence reflects something fundamental about the nature of intelligence itself. Maybe the development of advanced technology inevitably leads to transcendence beyond physical reality, with sufficiently advanced civilizations abandoning the material universe for virtual worlds or higher dimensional spaces that are completely inaccessible to our detection methods. In this scenario, the radio universe might be populated primarily by young civilizations like our own, species that haven't yet learned to escape the limitations of physical existence. The absence of signals from advanced aliens might indicate not that they don't exist, but that they've moved beyond the need for crude electromagnetic communication. Such transcendent civilizations might observe younger species with the same detached interest that we show toward ant colonies, recognizing intelligence but having little motivation to establish meaningful communication across such vast differences in capability and perspective. The cosmic silence forces us to confront uncomfortable questions about our assumptions regarding intelligence, technology, and communication. Perhaps intelligence is far rarer than we expect, requiring such specific combinations of environmental and evolutionary factors that it occurs only once in billions of star systems. Perhaps technological civilizations are intrinsically unstable, burning out quickly in nuclear fire or ecological collapse. Or perhaps the galaxy is indeed full of intelligence, but intelligence so alien in its motivations and methods that we wouldn't recognize it even if we encountered it directly. The signals we're searching for might be there, embedded in cosmic phenomena that we've catalogued and studied for decades without recognizing their artificial nature. The search for extraterrestrial intelligence continues, despite the cosmic silence, driven by the recognition that even negative results provide important information about the nature of life and intelligence in the universe. Every star system we monitor without detecting artificial signals helps constrain the frequency and characteristics of technological civilizations. But the silence also reminds us that we might be searching in a universe that's far stranger and more complex than our current theories suggest.